Hi. So in the last video I did, I discussed pressure and the relationship between pressure, force, and area. So if I have, for instance, a textbook here, and I push on this textbook with some force, and that force is distributed over the area of my hand that's in contact with the textbook, then the pressure that I'm exerting on the textbook is equal to the force that my hand is pushing with divided by the area of my hand. So that's just a reminder there. And the units for forces are the pascals, our pascals. All right. So we are going to take this and try to do something else with it. So in this particular picture, we've got a swimmer that's underwater. And we're specifically interested in the force that the water is exerting on the back of her hand. So we're given a couple of things. We're given the pressure of the water pushing on our hand. We're told the pressure is 1.2 times 10 to the 5th pascals. And we're also given the surface area of the back of her hand. We're told it's 8.4 times 10 to the negative 3 square meters. So we want to figure out the size of the force that the water pressure is exerting on our hand, as well as the direction of the force. Okay. So you might already guess that if her hand is like this and the water is pushing on it, then of course the force the water is exerting is downwards. So let's take a look at the numbers here. All right. So I can take my equation, my P is equal to F over A, and rearrange it so that I've got force is equal to pressure times area. Then when I proceed to plug in the numbers there, I get 1.0 times 10 to the 3rd newtons. Okay, well, that's great. 1.0 times 10 to the 3 newtons. That's in scientific notation, which is perfectly fine, but sometimes we kind of lose a feeling for exactly what that means. This is equivalent to 1,000 newtons. Okay, all right. So it's 1,000 newtons worth of force pushing on the back of her hand, which sometimes we have difficulty understanding exactly what things mean. Well, what if she were out of the water and she wanted to, I don't know, put something on the back of her hand that would have an equivalent weight to that 1,000 newtons? So how massive would that object have to be? Well, let's see. Weight is equal to mass times gravity. So our weight is 1,000 newtons. Gravity is 9.8 meters per second squared. So the mass would be roughly 100 kilograms. Wow, that's incredible. To think that the size of this pressure force is equivalent to the weight of a 100 kilogram object. Now, we've all gone swimming before. We've all been underwater. Well, I shouldn't say all, but most of us have been underwater. And while we might have noticed the pressure on our eardrums, we certainly didn't feel like we were being crushed, which you can imagine if you had a 100 kilogram object on your hand, you would, that hurt. That's 220 pounds. So what's going on here? Because this is what the numbers give us. It's correct, but yeah, it may be a little bit not understandable. Yeah, whatever. Well, what's going on is yes, we do have this pressure pushing in from the outside of our bodies, but we've also got, some pressure inside of our bodies. So we are acclimated to air pressure, the air pressure that we walk around in. So if we weren't, then our bodies would be crushed just because of the weight of the air pushing down on us. But instead, we've got an equal amount of pressure outside of our bodies to the pressure that's inside of our bodies. And so it all balances out. This is true as long as we're in air. But when we get in the pool and we start diving down deeper and deeper, maybe you've had this experience where, your eardrums start to hurt a little bit, or you feel pressure in your eardrums. Well, yeah, the deeper down we go, the more pressure is on the outside of our body, and the pressure on the inside of our body is, well, basically, the pressure that we walk around in, air pressure. So there's a pressure difference there, and that's actually what causes the issue with what we feel in our eardrums. All right. So let's move on and talk a little bit about this air pressure. Okay. So atmospheric pressure at sea level is 1.013 times 10 to the 5th pascals. This is, if I were to write this out, and that looks like a period, it was supposed to be a comma, that's 101,300 pascals. So just writing it out instead of having it in scientific notation. So that's normal air pressure. For instance, that's approximately the air pressure that I'm sitting in right now. So if we think about that air pressure and then just select out a random, I don't know, square of land where that square is, I guess, 1 meter by 1 meter, so that the area of that square would be, well, 1 square meter. Let's think about the force that the air is actually exerting on that square meter. Well, force is equal to pressure times area. And so if we think about this, then there's a 101,300 pascals, and the area is 1 square meter. So what do I get out of this? I get out 101,300 newtons. Holy cow, that's a lot. What does that mean? That means that the force that the air pressure is actually exerting on the ground is equivalent to the weight of a 10,000 kilogram object, which again is huge. Air pressure is tremendous. It's it creates a tremendous amount of force. And if it's not balanced, things get crushed. This is exactly what will happen if we have, say, some can, which you can see the crumpled can, the can right there. If we have some can and we evacuate it, we take the air out of the inside of that can with a vacuum pump. If we do that well enough, the pressure inside the can will be reduced enough so that the air pressure outside the can actually crumples it because of the difference in pressure between the outside walls and the inside walls of this can. Okay. All right, so let's see here. Let's see what we can do, maybe one application of air pressure. Oh, sorry, I jumped the gun there. This goes back to the last video that I did. In the last video I did, we found that the pressure underneath a 70 kilogram person who's balancing on 1 foot, the pressure under their shoe was equal to 34,300 pascals. And that's just the pressure due to the person's weight. But if I were also to consider the contribution due to the fact that they're standing in some atmosphere, maybe at sea level, then the total pressure would be equal to the pressure that the person exerts on the floor plus the pressure due to the atmosphere. Say, there's air pressure pushing down on the person's head. So that's all going to add together. And what we end up with here is 34,300 pascals plus 101,300 pascals. And I get 135,600 pascals as my total pressure there. Okay. All right, so that's actually, that would be the total pressure underneath a person's foot. That takes into account the contribution due to air pressure as well as the person's weight. Now, 101,300 is the pressure at sea level, but maybe you're not at sea level and maybe you'd like to know what the pressure is where you are. So there's this app called the Physics Toolbox Suite, which you can see those words down at the bottom of the screen there. This is available both on Android and iPhone. And one thing we can do with this, we can do a lot of things, but one of the things that we can do is actually a barometer. This is what it looks like right there. Let's see if I let this balance out just a little bit. And then I move this up a little bit. Now I move this down a little bit. Well, I guess the effect is not that great. We can see a dip. We can definitely see a dip. Up, down, Let me move this way up here, and then way down here. And let's see the result. Oh, there we go. There's that huge spike that you see now that's going across the screen. So we can see differences in air pressure based on basically where this phone is relative to the ground. So the closer I get to the ground, the more air is pushing down on the phone. The higher up we get, the less air is pushing down on the phone. While atmospheric pressure at sea level may be 101,300 pascals, here in my office at Radford University on the third floor of my building, it's currently 95,950 pascals. All right, but in most cases, that number for air pressure at sea level is going to be good enough for problem solving that we'll do unless we're told otherwise. All right. Let's proceed on here. Okay. So this is one application of air pressure that maybe we haven't thought of. It's a suction cup. It turns out that a suction cup doesn't actually stick to surfaces. The reason why a suction cup stays in place is because of differences in air pressure on the inside of this suction cup versus the outside of the suction cup. So what we're going to do in this problem is we're going to picture a suction cup, and we are going to take and stick that suction cup. We're going to take and stick that suction cup to the top of the ceiling, or I guess to the ceiling. I should just say that, to the ceiling. And then we're going to figure out, well, how much weight can I actually suspend from that suction cup before this thing falls off. All right. So I'm going to use some approximations here. I'm going to say that all the air between the suction cup and the ceiling has been pushed out. I guess that's, and also that we're at sea level. I guess that's my other approximation. So let's start with just a kind of a simple sketch here, try to understand what's going on. We've got our ceiling. There's our ceiling. We've got the suction cup, and then we are going to suspend a mass from that suction cup. Okay. And we want to figure out, well, how big a mass can this be? All right. So we've got a couple of different things here. We could have a force due to pressure on the top surface of the suction cup pressing down. We could have a force due to pressure on the bottom side of the suction cup pushing up. What other forces could we have? We could have, well, we do have a weight force, mg, from our mass that we're suspending. And then let's see, if I just have the suction cup up there by itself with nothing hanging from it, I'm going to have all kinds of force pushing upwards on that suction cup because of air pressure. So much force, in fact, that if it weren't for the ceiling there, it would just move upwards. So let's see, I've got a contact force there between the ceiling and the suction cup, and a contact force between two surfaces, to remind you, is called a normal force. So let's see, if I don't have everything completely balanced, don't have the maximum size mass on there, I would also have a normal force here that's downwards due to the ceiling pushing downwards on that suction cup. Now let's see if there's some things we can get rid of. Well, first off, I said that we're going to maximize the size of that mass. So we're making that mass heavier and heavier and heavier until really the ceiling doesn't have to push down on the suction cup at all anymore. As a matter of fact, this thing is about to fall off. So our normal force is going to go to 0. It's just going to disappear. What else? I said that the area between the ceiling and our suction cup was evacuated of air. All of the air is pushed out. So that means that there's no pressure between the suction cup and the ceiling. So our force there from air pressure on the top surface of the suction cup is 0. All right. So from what I've got drawn now, let's try and do Newton's second law. We've got, this is in some ways, I've got 4 red arrows on there. Those 4 red arrows are what? Our free body diagram. And now we're going to take our free body diagram and apply Newton's second law to it. This says the sum of the forces is equal to mass times acceleration. Well, first off, we don't want this thing going anywhere. Acceleration is going to be 0. We want it to stay stuck to the ceiling. And then what forces do I have left? Well, I've got a force due to air pressure pushing on the bottom surface of the suction cup. Okay, that's an upwards force. Okay, that's this one. There we go. And then I've got a downwards force due to this mass that I've suspended from the suction cup. Okay, and those are the only 2 forces that I have because there's no air between the suction cup and the ceiling, so there's no force of pressure on the top surface of the suction cup. And also we've made this mass large enough so that our normal force, our pushing force of the ceiling pushing on the suction cup is 0. All right, so let's proceed onwards. The force due to pressure is pressure times area. Okay, all right, F is equal to PA. And then I've got minus mg here is equal to 0. Now, if I rearrange this equation, I will get that mass is equal to pressure times area divided by g. And let's go ahead and plug in some numbers. 101,300 pascals is the pressure. Area, what should we do for area? A suction cup has a circular shape, so we need the area of a circle. This is pi times the radius squared. It's a 2 centimeter radius. Of course, we don't operate in centimeters, we operate in meters, so we need to convert that. So 2 centimeters is 0.02 meters. And then we're dividing this by gravity. This is 9.8 meters per second squared. That is, sorry, I'm having a little bit of difficulty there with my screen. Let's see if we can erase this and actually get the units on there right. Meters per second squared. There we go. And so when I stick this into a calculator, I get that I can suspend a mass of 13 kilograms. 13 kilograms from my suction cup. So, well, is that reasonable? Well, let me show you here. There between the end of that ruler and where my finger is, that's 4 centimeters. So that's the diameter of this suction cup. And so we're talking about a suction cup that's about that size, I guess about the width of my nose or something. I've got a pretty wide nose, but anyway, so it's a suction cup that's that size, and we're hanging 13 kilograms from it. 13 kilograms, what is that? That's 28, 29 pounds. That's like a toddler. So yeah, suction cup that size, and we can hang a toddler from it. Well, you know, that's what the numbers give us, but that doesn't really seem all that reasonable. Why is that? It's because we can't get a perfect vacuum in between the suction cup and the ceiling. But this does at least give us an idea of how to treat objects when we've got different pressures on either side of an object. And this is, in fact, how suction cups work. Some of the air is pushed out of the volume of space between the thing the suction cup is stuck to and the cup itself. And then as a result, we've got a pressure differential. And so it's that pressure differential between the size of the suction cup that actually causes it to stick to surfaces. It's not that the suction cup is sticky, it's a difference in air pressure, which I think is pretty cool. You know, if you've given it some thought, maybe you knew that already, but maybe that's new information to you, which, you know, I think it's pretty neat to understand how something kind of as ubiquitous, as common as a suction cup actually works. Anyway, if you look up on the internet, you can actually go find some YouTube videos that show people climbing up, sides of buildings with suction cups, with vacuum cleaners or modified vacuum cleaners that they actually can climb up a building just with that, and on glass surfaces. So it's pretty cool. These links aren't going to work in this video, unfortunately, but you can, I'm sure, Google, go to YouTube and search, I don't know, vacuum cleaner climbing building or something like that, and you'll see some results. All right, so let's move on to something else. We're going to look at how the pressure varies in a fluid with respect to height. So say we want to compare the pressure at one height in a fluid to the pressure at another height in the fluid. Now, first off, let me remind us of what a fluid is. When we hear the word fluid, maybe we just think of a liquid, and that's what we think of when we hear the word fluid. So we picture water or something like that, liquid form. But it turns out that, of course, it's not just liquids that are fluids. Gases are also fluids. So while the walkthrough I'm about to do is specifically for a tank of water, it would work in a gas as well, as long as the gas has a uniform density or a fairly uniform density. All right, so we've got a container of water here there on the left-hand side of the screen. And what we're going to do is look at just an imaginary volume of that water. So we've got basically like a rectangular prism there that's pulled out. And we're going to consider all the forces that are acting on that volume of water inside that rectangular prism. Well, on the top surface, we're going to have the pressure from the water above it pressing down. Okay, and then on the bottom surface, well, we've got a pressure of the water beneath it pressing up. If that might be kind of weird to think about that, but if that pressure weren't there, then this water would just fall down, and that doesn't make any sense because there's stuff underneath it, kind of like a normal force, I guess. So we've got these two different surfaces, both have pressure on them, pressure at the top, pressure at the bottom. And then also we've got the weight of the water itself involved. All right. If we sum up all these three forces, they should total to zero. And that's exactly what we see here. We see that the pressure at the bottom, there we go. The pressure at the bottom times the area. Now remember that force is equal to pressure times area. Okay. So when we've got P times A anywhere, we should keep in mind that P times A is force. There we go. So we've got pressure times area is equal to pressure times area plus mg. Okay. And what I'm going to do here is, instead of having 2 and 1, I'm going to replace this. Let's make this pressure at bottom and pressure at top. Okay. Because those are the two surfaces, really. It's the bottom surface and the top surface. Well, that's great, but maybe doesn't help us out so much. I've got an area involved there that I don't know anything about. I've got the mass of the water. What I really want to do is develop an equation that describes how these two pressures relate to each other. So let's start and try to work on this equation, this circled equation sum. So the first thing I'm going to do is I'm going to replace this mass with density times volume. Remember that density is equal to mass over volume. And so I can rearrange that and get mass is equal to density times volume. So let's make that replacement. All right, so there we go. I've made that replacement. Okay, mass is equal to density times volume. That's that rho V is now taking the place of mass. And I would like to do a bit more work. Well, let's see, the volume of this rectangular prism right there is equal to the surface area of the top times the height of this thing. Volume is equal to area times height. That's what we've got right up there up top. I can fill that in, that AH, I can fill that in for volume. which is what I've done right here. There we go. And then, there we go. Okay. I can fill that in for volume. And then I notice that I've got area as a multiplier in every single one of my terms. So I can divide through by area, and I will be left with this expression down at the bottom. And again, I'm going to replace that 2 with bottom and that 1 with top. And so I've got an equation here that relates the pressure at 2 different levels in a fluid to each other. So the pressure at the bottom is equal to the pressure at the top plus rho GH. That says rho HG, but same thing. That rho there is the density of the fluid, and the H is the, well, the height difference between our 2 points that we're interested in. Right. So let's take and apply this to a problem real quick. We've got, I don't know, a pond, a lake, something here. And we're interested in the pressure down here, 5.5 meters below the surface of the lake. All right, so let's see here. The pressure at bottom equals pressure at top plus rho GH. Okay. All right. So let's see. I guess the top would be the top surface of the water would be the top surface, the surface of the water. So what's the pressure right there? Well, that's just atmospheric pressure. So our pressure at the top is going to be atmospheric pressure. This is 101,300 pascals. That's our pressure at sea level. And then I've got density. Let's see, the density of water. Let's see, if I go back and I look at a table, density of fresh water, which I guess we'll make that assumption, is 1,000 kilograms per meter cubed. G is 9.8. And H is 5.5 meters. Okay. Now, when I multiply everything together, I get the result, right there we are. I get the result that the pressure at the bottom, the pressure at A, that our point that we're interested in is 1.55 times 10 to the 5th pascals. That's going to be our pressure at A. That's also going to be the pressure at B. So in both cases, it's 1.55 times 10 to the 5th pascals. Why? Because they are at the same level. Okay. If I was looking at maybe different levels, then our pressure would definitely be different. If I've got maybe, things, points that are at the same height, and there was a pressure difference from here to there, then some of the water would flow over that away until the pressure equilibrated. So the pressure at any height is going to be the same. So at both A and B, it's 1.55 times 10 to the 5th pascals. In this case, that's roughly 1.5 times atmospheric pressure. And again, this is why when we dive down, we get that pressure buildup on our eardrums. All right, that does it for this one. Thank you very much.